traffic flow on roadways. Dr. Rowett is also an expert on large-scale transportation system modeling and statistical analysis methods for extremely large data sets. An example of extremely large data sets that are very relevant to transportation systems is origin and destination transportation models that have many data points.
Or introduce the education background and previous appointment of Dr. Rowett. Dr. Rowett got his bachelor and master's degree from University of Waterloo at the same year, and got his PhD degree from Queen's University in 1992. Since 1992, he started his academia career from University of Alberta and was promoted to the associate professor in 1995. Since 1995, Dr. Rowett moved far south from Canada and started teaching at Texas A&M. And after about 10 years living in the subtropical area, he decided to go back to the north and start his appointment in University of Nebraska-Lincoln and hold the position of the director of Nebraska Transportation Center. And during the past 20 years of academic career, Dr. Rowett received a lot of awards both in research and teaching. And the most recent one is the UNL College of Engineering Faculty Service Award in 2008. It's our honor to have Dr. Rowett to give us a talk on his most recent work on calibration, model calibration. And please join us and give a big warm welcome to Dr. Rowett.
That in. Well, thank you, John. Thank you, Robin. So, John, where should I stand? Where's the best place? Is this okay right here? Okay. So, I'm happy to be here today. The first thing you notice, Tom was a bit different. I was asked to talk briefly about the Nebraska Transportation Center and the Mid-America Transportation Center. So, the Nebraska Transportation Center, what we do is we're the umbrella organization for transportation research at University of Nebraska. So basically we go out and find funding. We have about 50 faculty of varying levels of interest in our groups. Some, like myself, we just do exclusively transportation, and then others from the business school and college education, and maybe have one or two projects. Right now we have about $23 million in funding. It works out to about $7 million in expenditures. For students, that's probably, it's not really relevant other than we have a lot of projects and we fund a lot of students. We have about 60 grad students and about 60 undergraduate students funded this fiscal year. And we get about half our money from federal, half from state, and then about 10% from private. And then one of our vans that we use to help collect data, some of the data you'll be seeing in this presentation. We're also, like University of Washington, we're home to a regional center. Our region is 7, so it's Nebraska, Iowa, Missouri, and Kansas. And you can see that we have basically all the Tier 1 universities as part of our consortium. And again, we do, over the entire consortium, over the last few years, we've done 115 funded research projects, about $4 million in federal funds, about $8 million in matching funds. And again, the important thing for us is how many students, and right now we've had about 143 and 44 undergraduate students funded through our program. So it's a very student-oriented UTC. Sure can. Okay, is that okay? That's better? Okay. So Robin, you have a loud voice. Our focus is on improving safety and minimizing risk associated with freight movement. So we will have transportation issues. They are not related to passenger for the most part. Most of them are related to freight. And so a lot of our focus is on bridges, on rail freight, on pavements, those types of things. We're really happy. We just moved into a new space, a new building. So like this one, just completely refurbished. We have about 20,000 square feet. We have a couple core facilities. One I'm very happy with is our ITS lab. This is a before picture. But what we're going to use this for is to connect to our test beds that you're going to see in my presentation today. So we have a railway test bed, we have a freeway test bed, and we have an arterial test bed where we put out all kinds of ITS equipment, and we can test different different technologies. We can do it over time in different types of weather. And we're also connected to the state DOT and the city network, so we can get the video feeds, much like is done here at the university. And there's a picture of it. We're actually starting full build out, and the video wall goes up in 2 weeks. So we're pretty excited that we're finally going to get the equipment in to do the work. We do all kinds of things. We work with teachers. We work with students. We have a summer institute that we've worked for 6 or 7 years, where we work with teachers and students trying to get transportation into our curriculum in the middle and high schools. We have an after-school program that's been around for about 3 years. It's expanded to 12 schools in 3 different states. Very, very successful. What's nice about this from a student perspective is we actually hire students to go work with the schools in the after-school program. So the students will go work with middle school, high school kids on these really hands-on experiments, and hopefully get them interested in staying in the STEM fields. We have an intern program, I think very traditional in most UTCs, where we try and we find students and we find companies that would like to hire students, and we probably have about 40 to 50 interns a year across our region through our program. We also have a scholars program where we look at getting underrepresented groups and interested in transportation going on and pursuing advanced degrees. And we run that every summer as well. And this last year, we started to videotape all our presentations. We're going to put that on the website. Any student anywhere can benefit from it. And we do grant. We were talking earlier today about sharing courses. We do a lot of shared courses. For example, we have a railway course that we share amongst the universities. And I think that's going to be the future of a lot of the things we're doing. It allows us to get courses we might not have been able to offer at each individual school throughout the consortium. And not similar to this, we run a webinar series. Every one of our research projects in NATSE eventually gets a webinar, and we run those. We're going to set those up bi-weekly now. And it's quite interesting. We tape the webinar. We actually get more hits once we put it onto the web through Vimeo or off our website than we get at the sites, and we do get a lot during this webinar. We actually get a lot of feedback. So it's one of the ways we're using to communicate a lot of our results out now. And of course, social media. We use SlideShare and Vimeo. So almost anything we do research-wise gets put onto our web, but also out onto the social network as well. So a lot of changes. Very quick overview, but what I really want to focus on our lessons learned for us is really about the partnerships. We work on different colleges. We work across different universities. We have a huge private and public sector partnership as well, and that's led to a lot of the success of our center. And I don't think it's any different than in Region 10. I think when I hear and I've seen what you folks are doing, very similar in terms of attitude towards getting students involved. And okay, can't be that difficult. Sorry about that. So in terms of getting students involved and getting interactive with the profession. So what I'll talk about today is, and I want to go into the point of the talk, which is to talk about microsimulation modeling. I'm going to give a quick overview, and then talk about what I mean by calibration. And as I discussed from the beginning, what I want to do is sort of go over the past 10 or 15 years of work that we've done in this area and really focus on lessons learned. So it's something that's going to be pretty straightforward for some of you. It may not go into great detail, but I really did want to focus on some of the things that we've been working on. So for transportation models, I'm sure you're all familiar. We have macroscopic HCM models, vehicles per hour. What I'm talking about is microscopic, where we look at the individual level, whether it's a vehicle or a person. Sometimes that includes mesoscopic, which has some combination of the two. But for today's talk, I'm going to really focus on the microscopic models. And this is a kind of typical information flow on our models. We have supply information. We have demand information. In this case, it's going into a microsimulation model where they model the interaction between the two. and then we get some output. And pretty standard approach to things. The supply, the way I define supply is the network attributes, so the infrastructure, the operating strategies, basically anything controlled or under the control of the decision maker, right? Where do we put our roads? How many lanes? What's the traffic signal timing? So that could be anything, right? Number of lanes, lengths, curvature, channelization. And it's very traditional. I just took a screenshot of one of our networks where we have freeways and arterials. Within that, of course, we also have the control data, traffic signal timings, how much green time, what's the cycle length, all those things. Is there a managed lane or not? On the flip side is the demand. And you get to put the demand in a variety of ways. Most will be talking about origin destination matrices, where people are coming from and where people are going to. I'll be talking about the Nebraska model. We have a model of our entire freeway system in eastern Nebraska, went over on each arterial to the nearest traffic signal. So it's about 70 miles. Even this simple model of 145 origins and 145 destinations has about 21,000 OD pairs. On our links, we have 6,800, so we're highly underspecified. We're trying to get these things. It's a highly underspecified problem. We can collect 68 pieces of data, but we're trying to estimate 20,000 things. It can be kind of complicated. And I'll come back to that point in a minute. Many other attributes with it, number of vehicles, vehicle types, all of those things. So we have our supply, we have our demand. Demand and microsimulation models can sometimes be put in on the simple models, its entry volumes and turn proportions, and those are the older style, or you can put them in as OD matrices. And it does make effect. This is one I use with our students when I'm introducing the topic. You could go out, as you can imagine, having 2 origins and 2 destinations, measure some flows, 1,000 vehicles, 2,000, and you can say, well, what kind of, how are those volumes? What's the OD? And you could say, well, there's one where you have 1,000 at origin 1, they're going to 1,000 at destination 1. You have 1,000 origin 2 going to 1,000 going to destination 2. Right? So very simple origin destination matrix. But also, you could quickly figure out, well, even for this simple network, there's another one out there where you have almost the opposite. Everyone from origin 1 is going to origin 2. Everyone from origin 2 is going to destination 1. And both will give you the volumes you see. The issue, of course, is if you're going to use a microsimulation model as opposed to a macroscopic model, it really will affect your results, right? The second one has a lot more merging and weaving involved than the first one. So how you define your origin destination is obviously going to affect your results. And of course, if you go with the older models where you say, well, I'm just going to put turn movements, right? I know 50% are going to go this way, 50% are going that way. It's a lot easier, but you're never quite sure what you're getting. Are you getting the first origin destination? You're getting the second one, or something in between? So you do lose a lot of control of that. You can actually get circling, where your vehicles just keep circling because they keep taking this proportion change. So you're giving out some information on interaction. So a very simple example, but it gets the point across that how you define things, how you define your supply, how you define your demand can and actually will affect the results. So a quick introduction. What I want to do next is talk about the interaction. So I'm not going to learn a great deal on the microsimulation models, but basically, the model individuals at the individual vehicle interactions. As they enter, they traverse the network, they interact with the traffic control, they interact with other vehicles, and then they depart the network. And this is a model that's somewhat small increments, typically 0.1 seconds, although different models do it different levels. And really looking at the internal processes, the driver's decisions, the vehicle characteristics, the signal operations. So getting back to that original diagram I had, right? We have these interactions: vehicle to vehicle, vehicle to roadway, vehicle to control device. That's essentially the microsimulation model in a nutshell. I'm going to try and run ours. And it didn't work. Okay, there we go. So here's a picture of, we just took one place out of this Nebraska mall. It's about 60 miles, so this is one of our interchanges. And they can get pretty, you know, they look great. This is VSIM, very good program. You can get it, you can make it look very nicely. You can do trucks, you can do cars. You know, we take these out and show people, and they like them. It makes sense. It looks nice. I think the real question though is, you know, how good is it? Right? It looks great. And the question we always have was, is it really doing what we want to do? And that's sort of the focus I want to talk on today. You know, if you're how accurate do you have to be, or how can you make this model as good as it can be? Is probably a better way of saying it. So you run the model, you get output, you can put it down, you can get a lot. You can pick a time interval. You get to decide the form and the frequency of the output. As you can imagine, there's three types. You can get point measures. You know, what's the speed at this point? What's the throughput at this point? Or these location of points? You can get link-based. What's the travel time on a link? What's the space mean speed? You can do corridor system measures. What's the average vehicle speed along a route or along a corridor? What's the speed along or travel time from an origin to a destination? You can get average person delay. There's all kinds of data you can pull out of these models if you want. The user gets to decide, and it makes sense. You have all the information from that simulation. You get to pick what you want. Of course, it can be overwhelming just how much data there is. So part of the thing you have to do as a modeler, of course, is identify how accurate the performance measure needs to be. Right, so you're getting this data out. How accurate does it have to be? And I'll come back to this theme as I talk today. And there's another caveat I always talk about. You know, you also have to understand what you're trying to do. Right, so we always talk about we want as accurate a model as possible. Sometimes it's not as critical to be absolutely accurately. You know, sometimes it's okay to be relatively accurate. So, you know, the question, does it all have to be accurate? Does them all have to be accurate? And the answer is, oh, we'd like it to be, but does it really have to be? And it comes down to what you're doing. So you can imagine you collected some empirical data, you have some simulated values, have a measure of performance, travel time. And you have two designs, and you're trying to decide, you know, should I do a managed lane or should I do this other lane? You know, should I just make it all free flow? And you have some performance measure. You can see that the simulated data in this case overrepresents what's actually going on. But the reality is the relative benefits of both, you know, whether it's observed or simulated, are the same. So sometimes, as long as you're looking at relative benefits, the model, whether it's a microsimulation or macroscopic, it may not need to be accurate. It just has to be accurate in terms of relative. It allows you to pick the right choice. So lessons learned, well, we do need an accurate model. We sure like it to be internally consistent. I always say it needs to fit the need, right? Is it planning? Is it operations? Are you doing safety? That it should model reality. And I'll come back to this last point at the very end of my talk. And the other thing is, as I discussed, we have lots of data on these models, right? We get a lot of data. And as the title of my talk indicated, well, we have lots of data. We have our ITS data. Okay? We can go on and collect. We have the ability to collect a lot more data than we did 20 years ago. In fact, we're collecting so much we're hardly using any of it. So what do I mean by ITS data? Well, I want to talk about the types and advantages, and then talk about how that relates to microscopic simulation. So we have point data, and I think you're all very familiar with that, right? We have video data, we have inductance loops. In Nebraska, we use a lot of radar to get our data. It's kind of interesting. Our state DOT gets their data for free because someone's gone in and put up all the radar detectors for them, and they just wanted permission to be on the right of way. They collect the data, they sell it to others, and then they give it to the government for free. Completely different way of doing things than I've seen in the past. And you get information like spot mean speed or throughput. Pull that one up. And this is from our test bed. It's kind of hard to see, but we do a lot of train data. We collect a lot of information on trains and arterial roadways located near trains, and we look at ways of optimizing traffic signals. But here's an example of using a detector to go out and get train speed. In this case, you can see it's about 18 miles per hour. But it gives you, at one point, things that are going on in the network. What's the speed? What's the volume? Those types of things. The second time is link-based, where you get it from point to point. We've done a lot of work with automatic vehicle identification. So here's a picture from some work we had from using toll tag technology in Texas, where vehicles with toll tags drive under an antenna. They get picked up. They get measured further on. Talk today about Bluetooth, right? Very similar technology. Cell phones. This stuff is coming more and more prevalent. It's a lot nicer because it gives you actual space, right? Information over space. What's the travel time? What's the space mean speed? What's the delay? Those types of things. We had a project in Nebraska where we were looking at actually putting RFID into our license plates. And this actually came about from the trucking associations, because they already have RFID on their trucks. They have license plates. They said, can't you put them together? Is there a way we can work together to work this out? So technologically feasible, politically I'm not so sure about. But you may see this in the future where our license plates actually have information on them, much more than just the visual part of it. Another example, this is a summer project we did about a year and a half ago. The commercial vehicles, if anyone's familiar with the trucking industry, has a lot of GPS data. What they do is they get information on where your truck is, they get information on where their engine is, what the engine's doing. Is the truck going fast? Is it going slow? Are they doing hard accelerations? Are they doing hard accelerations? So they monitor the drivers to make sure the drivers are where they're supposed to be and are driving the way they're supposed to be. And they have satellite uplinks, and they have very good detailed data on vehicle performance. If you want, if you're able to, you can actually get it by second, where travel, how much idling, all the things the truck is doing. And this picture is just one that I put in. This is this one little trucking firm in Nebraska where they went in a month over temperature. So we were interested to see what they were doing, how much idling they were doing, and where they were doing their idling. But once you look at this map, you quickly realize, there's a lot of information here that these trucking firms have that they're collecting, where their speeds are, what their travel times are. And they've quickly, the whole industry has basically set up a system where they take that information, they bring it to a central source, and they provide it to each other. So they actually have very good ideas of what's going on, travel times for trucks, delay times for trucks, where congestion is. They put out a top 20 congested list, and they give it to the government every year. This is where our trucks are having trouble. This is where you need to have your money. They put out maps on where their congestion is. So it's very interesting that this, we have this data we used to collect, the government used to collect, and now actually the private sector is collecting it, sharing amongst themselves, and using that for policy lessons. So lessons learned, there's a lot of ITS data collection historically by the government. What we're finding is the private sector, a lot of companies are putting that in, collecting the data themselves. Private sector companies are collecting the data themselves and using that and providing it to others. A lot of potential for private-public partnerships. What is important for this talk is there's lots of data and very robust data, individual, which mimics the microsimulation outputs. So not only just getting point stuff, we're actually getting link route type information, and that's pretty key for doing calibration. So you have more robust data of individual, allows you to think about things such as the mean, the variance, the distribution of data. And again, boy, if we have that, and that's what microsimulation gives us, it gives us an opportunity to compare how are our simulations doing to what the empirical stuff, and not just one measure, but maybe other measures as well. When I say lots of data, I mean terabytes. Even our model center, we have, our labs probably have right now 18 to 20 terabytes, and we're running out of space. And it's just the issue of how do you manage this data is, I'm not going to talk much about it today, just that we have data. Trying to get that data into information you can use is a whole other topic. How do you archive that? So I talked about the microsimulation, I talked about the data, now I really want to get to where the point of the talk, which is ITS data and microsimulation. So we talk a lot, when we talk about microsimulation models, or any model really, there's a number of terms we use. One is verification, and basically what that is just saying, is the model doing what it said it was going to do? And when I teach our modeling class, I always say, who's responsible if the model's wrong? Right? If the model's not doing what it's supposed to be doing, who's responsible for that? Anyone have an idea? It's actually the user, and most places will do that. You can't, as an engineer, go, well, the model said this, and that's why this happened, right? You have to kind of verify it.
So from the chat, we have a question. Basically, Bill Lake wants to know, are you doing any data validation or quality control checks?
Doing a lot. So the question is, do we do data validation? Almost if you're using inductance loop data or point data, you almost have to do that because of the drift in that data. So you can do things like, I measured so much volume here, I measured so much volume here. Did they match? And I can tell you a lot of times they don't. So that's a way of calculating whether one of the things are drifting or not. Almost without exception, the reason we set up those test beds in Nebraska, at least for our perspective, is we can go back and make sure the detectors are doing what they're doing. We have a visual count of what's going on and going through. So now, of course, this is more of a sampling thing than going through each detector. But yeah, we do that. And I think almost by extension, you have to do that. So it's a good question. So the verification we're looking at, is the model doing what it's supposed to? And as a user, you're supposed to make sure that it is. So basically, you're going through and deciding whether you're not really concerned whether the logic is correct, right? But whether if you said this is, for example, random arrivals, that the vehicles are actually arriving randomly. So you might say, see a stream of vehicles will follow a Poisson distribution. Verification is just going out and making sure that it actually is doing what the model said it would do. Calibration, the way I'm going to define it, it's really the process of modifying the input parameter values. So the parameter values in the model that you get to choose. So you're modifying them so that they accurately replicate the observed local traffic conditions. So again, I'll come back to this accurate in a minute. So we're comparing simulated and observed data. And of course, that's great. Yeah, we should compare our simulated results to our observed results. And then the natural question, well, what criteria do you use? What methods do you use? What statistical methods do you use? And then validation is looking at the underlying fundamental rules and relationships to adequately capture the targeted emergent behavior. So, you might look at the model and say invalidate it based on theory. It's doing what we expect it to do, some sort of internal validity. You might get empirically collected data and compare it. If you're using empirically collected data, it's important to use the stuff you didn't use to calibrate. So you have other data that goes through and says, yeah, we calibrated, we checked it against this other data set, and it appears to be working well. So getting to calibration, well, when you look at a simulation model, they have all kinds of parameters. They have lane changing parameters, car following parameters, gap acceptance parameters, and I just listed a few here. There's a large number. A lot of time users will just run the model with default values. Sometimes there's difficulties in collecting field data. They just have a lack of calibration procedures. I'm hoping to show today that it's probably a bad idea to do that. My experience has been that it rarely replicates field conditions to the point that some people would like anyways. And so a lot of our work is, is discussing ways of calibrating, but also showing the need for calibration and validation. So getting back to our diagram, so we have supply, we have demand, we have this microsimulation model, we have output. setup, well, go get some data. So you could go collect it yourself in the field. You could use some ITS data. What types of things can you use? We saw today you could use Q length, you could use speed, you could use travel time. Which one's best? Well, it depends, I guess, on what you're trying to model. Right? What is critical to you? You know, are you doing a safety analysis with your microsimulation? Are you doing a speed analysis with your microsimulation? You know, what exactly are you after? But there's a lot of things out there you could use. And then it comes down to, well, you want to do your evaluation. So you could run your model and you could compare it, whether it's speed or travel time. Standard one is something like this formula, you know, mean absolute error or mean absolute percentage error. There's a number of them out there. We use the mean absolute error ratio a lot, only because it gives a real physical feeling to what's going on. So if you look at the formula, you take your simulated output and you subtract off the observed and divide it by the observed. So it could be, you know, travel time on a link minus the, you know, simulated minus the observed travel time on a link. You divide by the observed, so it gives you a percentage you're off. You take the absolute value, so you don't worry about whether it's up or down. You're taking the sum of them and dividing by the number of ends, so number of links. So you might take every link, see what your observed was, what your simulated was, and this is actually a sort of a percentage error. So if it was 0.1, it means about 10%. You're off by about 10% on average over all your links. So that's the mean absolute error ratio, and I'll come back to that in a minute. And so you have your process, right? You run your model, you have your empirical data, you have your model output, you calculate your mean absolute error ratio, and you can say, oh, it's, you know, it's 10% off, it's 20% off. A second alternative is to go back and say, well, I can, you know, I have statistics, I have, you know, mean, I have a variance, I could actually do a t-test on it. Right? I could do a confidence interval on it and say, you know, statistically they're the same, or statistically they're not. So in this case, same diagram, you have your empirical data, you have your model output, you can do, you know, some type of confidence interval. And this graph, I'm going to apologize for the X and Y axis, but basically it shows on the Y axis the a flow rate, and this is from a freeway simulation. So on the Y axis is the flow rate in vehicles per hour. On the x-axis is a station number. So we had a couple places where we're collecting flow, both empirically and in the simulation. And we're just looking at what's the flow rate for this model. So the dark blue line is the simulated. The dotted blue line is the observed. And if you look at it, you'd say, well, maybe a good, you know, maybe it's close, maybe it isn't. But if you have enough observations, and I'll go back a slide, right? If you run your simulation model n times, you can get an idea of what your error bounds are. Similarly, you can go get observed data and get error bounds on it. You could go through, put in your confidence intervals, and you'll see right away, are they statistically the same or not? And if you look at this one, you can see that for some stations, yeah, they're within the error bounds. So it'd be hard-pressed to say they're not the same flows, given the data you have. Right? But others are clearly, they're out of bounds. And so you as a modeler get to decide, do I want them all within bounds, and I better make some changes so I can get them within the bounds, or I might be satisfied with that. But that gives you a statistical basis for looking at your results and going, yeah, I'm satisfied with those numbers. And that's why a lot of times, let me go back, we don't run the simulation model once, we run it a number of times to try and get the ability to figure out how much of those error bounds are we getting, how much variability in our answer is there. And if you don't like it, then you go back and you repeat it. You can adjust the parameters until the data matches, which makes sense. So you go back, you put a new loop in, you go back up to the simulation model, you make some changes to the parameter, you run the model again. Right? You just keep doing that until you find some reason to stop. You're satisfied with the numbers, it's within, statistically it's fine. You have a low mean absolute error ratio. So that's basically the calibration model right there. So you find the lowest mean absolute error ratio, you can run a t-test. quick question would be, why not all combinations, right? Why don't you just run every combination parameters and get that, right? That'd be fun. That'd be a good grad student project, right? So, you know, I'll take this, and you can argue there's usually 30 parameters you could change. And I'm not going to read these out, but there's, you know, there's a large number that you have the ability to change and affect the results. How do you get the key ones? Well, you can go to previous studies. You can use engineering judgment. You know, I'm interested in driver behavior, and this is what I'm looking at. So just going to worry about the driver behavior parameters. It could be vehicle characteristics, right? The vehicles there are from calibrated in this region of the country, and our characteristics are a different country, and our characteristics are different, so I want to calibrate to those. But even if you took VISM with 10 parameters and each had 5 values, it's probably about 10 million combinations. So the ability to go and do every combination is not possible. So I'm going to have to do some type of optimization. One caveat: where did the demand OD matrix come from? That sort of starts where I started from. I started off with this OD and said, these are difficult to get, even for a simple two-node example. I'm sure the students all know where the OD matrix comes from. And that's that second arrow coming back. We estimate. We get synthetic ODs. We estimate them from volumes. We have models for doing that. And where does the data come from? Well, it comes from the ITS data, typically, some type of volume, some data you're using. So you get this sort of double loop where you're using the empirical data to identify your OD, you're running your simulation model, you're getting your model output, you're seeing how good it is, you know, and then the question comes up, well, should I be optimizing on my OD matrix as well? Right? And we have done that work as well, and you really are into 2 types of optimization, right? You hold the OD constant, you optimize the simulation model, hold the simulation model constant, and optimize the OD. And I don't think there's a right or wrong answer on there other than to know the ODs are not easy to get, and they obviously are going to affect everything you do. And there's, you know, a lot of the work we do, I try and keep it simple so we don't have a large number of options on the ODs. So a lot of corridor work, those types of things. So calibration methods. When I started out doing this stuff all those years ago when I was in the student seats, we did it manually. It's better than the default. I will say it's tedious and time consuming. You can only do a small set of parameters. I don't recommend it because that's what we used to do. It was like, it would take you a month of playing around, hopefully kind of intelligently, running the model, seeing what the results were. And I say it took a month because that's probably what most people had, a month or 2 to try and get the model working. And they were much simpler. But when you look at that loops that I showed, you can certainly see, well, I could do that with a computer. Right? I can automate this process. In fact, with the, you know, if you have the right set of computers, you can send a simulation to each computer, run the computer, get the results, change things. And so that's sort of what we do. You could do an experimental design, and we certainly looked at using things such as lab square design, where you identify the combinations ahead of time. So instead of 10 million, you're doing, you know, 300, 400, 1,000. What we tend to use now, though, is more of an optimization function. So we've identified what our objective function is. It could be lowest mean absolute error ratio. It could be something like 90% of link travel times or within the empirical confidence intervals, something like that. The optimization, there's a whole bunch out there. There's reduced gradients, simplex algorithms. I've used all of those. I'm going to talk today about genetic algorithms because it's been a fairly popular one. But I will say that almost any of the ones we've tried have all come up with good answers in the process. So there wasn't any of those that we've used and we said, oh, that's awful. We shouldn't do that. So I'm going to do a calibration example for you. Okay. So we take our traditional measures of similarity. I'm going to pick the mean absolute error ratio that I showed earlier. First question, what are you interested in? Are you interested in the mean? Are you interested in the distribution? Right? If you're going to And the answer is always, well, what do you want from your model? Do you want to just get an average value? Do you want to get the distribution? Are you interested in reliability, the distribution of speeds? Are you happy with just the mean speed? Are you interested with the 85th percentile speed? You know, that's the sort of question you have to ask yourself before you do the calibration. That's going to define, you know, how detailed do you want this. In this case, I'm going to talk about, I'm going to look at the closeness of the observed and simulated travel time distribution. So I've made the choice that I'm interested in the distribution of travel times. That's what I want my model to be able to replicate. When you're looking at distributions, you can't use, you know, basically, if you remember from your statistics, you can't use a lot of the statistics that you learn in first and second year stats classes because they assume normal distributions, normal assumptions, and that doesn't apply to a lot of distributions. So yeah, there's other things you can use. You can use a Wilcoxon test, a KS test. You can pick one, pick all of them, right, and run through it. So here's an example. This is from Houston, Texas. We looked at an arterial, major east-west arterial, 4 intersections, 3 signalized as part of the Houston Bus Priority Project. Okay, so we're looking at a fairly small corridor. We want to calibrate the model to see how that bus operates. We were doing it in VISM. We looked at a number of parameters. Here's the empirical travel time. So on the y-axis is frequency, on the x-axis is travel time in seconds along the corridor, or what we're interested in. And you can see we've got a histogram of the travel times of vehicles on that link. And you can see it's bimodal. And it's what you'd expect in an arterial system with traffic signals. All this says is some people make the light, the green signal, and they go right through, and others get stopped at some point, and they have a larger delay. So it's a bimodal distribution, and this is for the morning peak. So here's our calibration process. We pick a genetic algorithm as the optimization. We're going to use the Kolmogorov-Smirnov test and the Wilcoxon test to see whether the distributions match. Okay, so we're going to run our model. We have the empirical data. We want to come through and we want to find out, can we calibrate the models? Can we adjust the parameters so that what the model is outputting is what we're seeing in the field in terms of distribution? And you can imagine if we're doing the distribution, then the means will also be correct, right? If you're getting close to the distribution is correct, the measure of central tendency will also be close to correct. Okay? So that's our process. We run the simulation model n times, so it really depends on the metric, and we usually pick 10, and that seems to work well. But again, it depends on how accurate you want your calibration to be. So here's our automated procedure. I'm going to go through this fairly quickly. You have the genetic algorithm, you have an initialization. You pick a bunch of potential parameter sets that could work. You could pick them through engineering judgment. You could pick them from previous work. You could make them up randomly. In our case, we picked 30. And I'm not going to go into the details of the genetic algorithm, but there's ways of you picking numbers that these, like the mutation probability and crossover probability, that are going to give you new parameter sets. So you pick a set of parameters, you run the micro simulation, and you get results. Okay. You then compare the results statistically. So use those KS tests and the Wilcoxon test, and you say, well, of all those 30, did any of them pass our test? And basically the way the genetic algorithm works is if they did pass a test, they have a higher chance of being adjusted and sent in for the next iteration. And we'll run this over and over again. So we run some tests, we get some mutations to our parameter set, we change the parameter set in some way that mimics biology. We get new sets, and we just keep running this over and over. In our case, we did 100 iterations. And the idea is that if something's good, you continue it to be good, but you do have some randoms to see if there's maybe somewhere else that you can get better results. So that's the genetic algorithm, and like I said, you could use a simplex algorithm. There's a number of optimization to mimic this, to change this thing as you go through. The next thing is from a student's point of view, right, you push the button once, and it just does it. And like I said, if you're doing this by hand, it's not any fun. But this allows us to do thousands of these runs and look at it. You know, we're not doing all, you know, we're not doing a million, all different combinations, but we do get to look at the sample space and try and find ones that work. So what are the results? Well, the first thing was if I just ran the model with the default parameters, so I just took Visum off the shelf and ran it for this network, there was a 21% mean absolute error ratio. So on average, the travel time was off by 21%. This is actually a really good number. We've run it where it's been off 100, 120, 130, just taking the default parameters. But here are the results. So this is a graph. On the y-axis is the mean absolute error ratio. On the x-axis is a p-value from the KS test. Basically, anything high is good. So the black squares are good. The orange circles are bad in terms of the statistical test. Okay? So basically, I took out all the runs we had, plotted them. I cut it off at 0.3 because there's some horrible ones, but these are the ones that you may be interested in. If you look at the acceptable range, those black squares, your mean absolute error ratio ranges from about 0.7% to about 7%. So you can have a mean absolute error ratio of 7%, but it's still acceptable statistically. And the other thing you're going to note is there's a large number of acceptable results there. If you look at those black squares, if you're saying statistically, is there a difference between what I observed and what I'm simulating? There's a whole bunch of parameter sets that give you statistically significant results. And then the other thing I want to point out is that there are some parameter sets, a whole bunch of them, in that green circle, where they had really low mean absolute error ratio, almost zero. I mean, the absolute error in the travel time, the mean travel time was almost zero, but they failed the statistical test, right? And it kind of, you could say, oh, that makes sense. The mean absolute error ratio is looking at the mean, the average, and the statistical test is looking at the distribution. Okay? So you could have a test with a really low mean absolute error ratio, but it might not give you the results you want. It may not be the set you want. And this is what and this shows you that same thing. So if you remember the first diagram I showed you, which was bimodal, we have two graphs here, both with a 1% mean absolute error ratio. So they're off by 1% in terms of travel time from the results. The one on the left is rejected. The one on the right is accepted. And the reason you can see that and when you look at them quickly, you can say, yeah, I can see the one on the right looks more similar to what our empirical data was. Okay? It has a clear bimodal shape, very similar to what we were seeing empirically. So again, how do you calibrate, right? Are you interested in the mean? Will give you a different result than if you're interested in the distribution. Then the next question, of course, is, if all these, if I have all these statistically significant ones, how do I pick the best one? And, I don't think there's a good answer. In this case, we looked at the saturation flow rate that emerged from the model, compared it to the HCM. And we said, well, we'll pick one that's close to what we think the saturated flow rate should be. But I think there's lots of opportunities for doing that. So lessons learned, my big thing is, you don't necessarily have to use the default values. It might be good to go calibrate it at least some way. There is ITS data out there. You can do it statistically based. In this case, bimodal travel distributions. Simple metrics may not be enough, but you may have to do additional analysis for the candidate parameter sets. So there is a potential to use statistics to help you make the choice on the calibration. But it also brings up the question, if you have lots of parameter sets that are statistically, give you the same statistical results as the empirical data, how do you pick between those two? Okay. And what I want to do is finish off with one last example. So I started off talking about Visum, and I showed you a fairly sophisticated model. I want to talk briefly about CA models, cellular automaton models. They're very simple. Basically, they take a roadway, they compose of cells. Cell size is about 7.5 meters. The cell is either empty or occupied. The vehicles are moved through the network by cell rules, and I'll talk about them in the next few slides. And velocity is an integer number. So they say your vehicles can only go 0, 1, 2, 3, 4, 5 cells per second. If you take the numbers I have there, it works out to 0 to 135 kilometers per hour. That's a CA model. The rules, the first one, over time, you maintain your speed. So if you're at the maximum speed, so let me take a step back. So this is a CA model. On the y-axis is speed in kilometers per hour. On the x-axis is time in seconds. So it's just a model of a vehicle, one vehicle following these CA rules. What it says is if you're at a maximum, there's a probability of 1 minus p noise that you'll continue at that maximum speed. And there's a probability of p noise that you're going to drop. So you can see at point A, the vehicle is maintaining it. At point B, it suddenly drops 1 cell per second, and then it goes back up. So there's a probability that you're going to maintain your speed. There's a deceleration rule. Basically, you can't hit anyone. So if you someone pulls in front of you or you come up on them, you can decelerate. It's a function of the gap size and that p noise. And you can see here that this vehicle went from 110 or so, 115 down to 0 in the space of 1 second. Okay, so that's a CA model, and you can see that point. And we set it up, we pull the numbers out. Yeah. And then it is, if there's an acceleration. If you're going slower than you want, than the Vmax, you can accelerate if possible. So there's no way to you. There's a probability at every time step of increasing, and there's a probability of maintaining your speed. And you can see that the vehicle that accelerated at A is moving up at B at stated speed. And so it's a random thing. And it's all one parameter, p noise. Okay. So you now know everything about cellular automaton models. They're very fast because they don't really worry about, what's the vehicle, how did it be doing, is it slowing down, like keeping a safe driving distance between them. So it's a CA model. It's also called particle hopping models. They're very granular. And here's an example: speed, kilometers per hour on the y-axis, time in minutes on the x-axis. And you can see the vehicles are going from 110 to 0 in a second. They're hopping around. What the models would say is, well, yeah, that's not realistic, but on average it is. So you say, well, does this thing work? And so what we did was we simulated a freeway in Houston, Texas, Interstate 10, fairly major highway. We got empirical data. We went through and we said, let's just run a cellular automaton to see how it goes. And then we plotted it, 15-minute or 20-minute plot. So we took the data, we listened to the modelers who developed it. They said you can't use the individual stuff, just take aggregate. And you see on here speed on the y-axis, kilometers per hour, flow on vehicles per hour per lane on the x-axis. And that's what the model looks like. So what do you think? What do students think? Yeah. Looks like your first year of traffic flow class, right? It's one of the first diagrams you saw. And you're like, yeah, that looks good. I would never have predicted what I just said 2 slides before would do that. Right? But it does. You can take the data because it's individual. Aggregated it 50 minutes. You could aggregate it 3 minutes. You could aggregate it 10 minutes. You could aggregate it 20 minutes. Of course, you still get the same. Aggregation won't change the flow. What do you notice about the capacity, though, or the maximum flow? Well, if you... That's right. So, it follows what we know, right? Why does HCM always have about 15 minutes? Because it depends on how you aggregate, affects your result. This is all the same data, I just aggregated it differently. If you pick 3 minutes, you get a much higher capacity than if you pick 20 minutes. with the same data. Why is that? Well, for 3 lanes, you can get a lot of flow, and then you multiply it by 20, you get a fairly large number. Right? So, again, for the students, there's a reason why I say pick a standard, right? Pick 15 minutes so you can compare apples and apples. So it shows what we know, and it's a model. There's that one parameter that does this. You can adjust the parameter p noise, and you get different results. So we ran through the model and just changed p noise, and we plotted, and we end up that as you're changing p noise, you can change your maximum flow rate. Okay. What's interesting about this model is we ran it on this network with one parameter. We compared it to the Houston empirical data we had. We ran VISM with 30 parameters, compared it to the data. And guess where I'm going with this? You couldn't tell the difference in the results when you calibrated them. They were not more accurate. Now, in fairness, we're not talking about a pipe. We're not talking about traffic signals and all those things. But basically, the one parameter model was as accurate as VISM for that pipe thing. I'm not saying that the CA is going to beat VISM. I'm not saying that one's better than the other. But it does come up with a question we always have, and I've always had, is how many parameters do you need to model your system, right? You saw the data, what is IPS data is really robust, but can we model that with 3? Can we model it with 20? Do we need 30? Are we fooling ourselves by putting 30 parameters in and doing all this calibration when really maybe we only need 3 or 4 models given the accuracy of our data? So I'll leave it as an open question. Given the accuracy of our empirical data, I'll come back to that OD, given the accuracy of our OD information, that's an open research question. And we certainly look at ways of trying to propagate those errors through the process. So thank you for your time. What I didn't cover today, I didn't talk about multi-vehicle calibration. We do this. We do calibrate commercial vehicle stuff. We try and look at classification data and WIM data and try and bring those into the calibration. We do multimodal calibration, trans and cars. We saw driving simulator today. There's big projects now on hooking up the micro-simulation models with the driving simulators. That's sort of the holy grail of that, so you can get driver behavior actually within the micro-simulation. It's a pretty neat approach to things. I didn't talk about the estimation of the OD matrix and the calibration of the micro-simulation model simultaneously. We do that as well. And I didn't talk about safety analyses in micro-simulation, another big field. There's just a lot there. I probably talked too long, and I apologize for that. But I think I'm taking a whole course and trying to get the lessons learned down to one lecture was a bit much. But the point for the students and everyone, there's a lot of open research questions in the micro-simulation field. The nice thing is we have the data now to try and help answer those. So lessons learned overall, very useful tool, micro-simulation. Know your application, know your data, calibrate and validate. I like to use them on statistical basis. I like using statistics to do that. Still lots of research questions. So on that, I'm going to end my talk, and I'll be happy to take any questions.
So when you were looking at the cellular atomic cell model,
Mm-hmm.
did you look at kind of like the cell transmission models as well, or with traffic signals in mind?
No, because we were just on that one. We were just on that very simple one. I think because it was a project that came to us on the CA, and I tell you, to tell you that I was very skeptical that these would work, and I ended up eating my words because they actually worked. Well, what it taught me was, which is why I think other people have had the same thing, is just it's an open question. How much parameters can you really do given the data we have? Right. And I'm not sure that there's an answer for that, but it's certainly a research one. But yours is an excellent one, right? Can you go look at the signals and see if that's, to me it's almost, the question is how many parameters do you need to do your application given your data? And are we really fooling ourselves when we put these other ones in? Yes, sir.
So I saw you use the statistics method.
Can you repeat the question when you?
Oh, sure. Great. Thanks.
So I saw you use the statistics method to get the parameter for calibration.
Mm-hmm.
So I wonder whether you also consider the driving behavior to the performance when you choose the parameter.
Yeah, that's a good question. The question is, we're using statistical methods to, let me paraphrase the question. So we're using statistical methods to do the calibration, but what about the driving parameters from each location, right? How do you calibrate for that?
Yeah, and when you put the calculator in system, that will be I maybe in one day, it's very different from.
Sure. Right. So so the question is, the driver behavior is different from city to city. I think the argument on the calibration is if you can get the travel times and you can get information like headways, and you calibrate, let's say, the headway, that would be the way of taking into account the different driver behavior. So calibrating a model in Lincoln, Nebraska should be different than calibrating in Houston, Texas, or Chicago in terms of how close the drivers drive to each other, how aggressive they are, those types of things, right? So the hope is that the empirical data you get or the ITS data you get and calibrate to captures the driver behavior that you're interested in. So at the end of the day, your parameters are, intuitively what you'd want is your driver behavior in Houston simulation is more aggressive than in a place where they have more gap time. That's the hope, and that's sort of that internal consistency I was talking about. Right? If you came in and calibrated your model as the opposite, you might not have a lot of faith in your results. Yes, sir.
Question. In this region, we do a lot of calibration to speed control.
Mm-hmm.
Is that something that genetic algorithm has ability to do?
Certainly. Yeah, we've done it. And the contour maps, right? Because essentially what you're doing is, I showed that one where you got stations, you just add a time dimension to it. The dilemma in all of this comes is the more dimensions you add, the odds of you hitting each one. And that's what I was saying. It may not be that you hit everything is statistically the same. You would have, I want 90% of them, but I sure want my freeways to be correct. I want my arterials to be more correct than my collectors. There's kind of a hierarchy in there, but certainly that's very straightforward to do.
A lot of it in this region, like interested to find out algorithms. So I think a lot of times we do some combination of manual, maybe sensitivity tests, but yeah, at higher level of precision is trying to identify bottlenecks, where the bottlenecks are in such a long corridor can be complicated, especially when they spill back through each other.
Yeah, absolutely. So the question, I repeat the question to the outside audience. So the question was, can we use contour maps to do it? And the answer is yes. And I'll just add on to my answer. And I should point out that at the end of the day, even though you run this automatic system, you still have to go back and make sure that it's, and I should make that clear, that you're comfortable with it, right? That the traffic jams are where you think they should be, that the behavior is where it should be. I don't think we'll ever get away from that. But I do think, when I talked about that there are multiple solutions that are statistically okay, that's where you can come and use your engineering judgment and say that these ones appear to be better than the other ones.
Another question from the chat, and they're asking, why in practice do we spend such little time on calibration? And the counterpart question, how much time should we spend calibrating?
Those are good questions. So the first question is, why in practice do we spend so little time in calibration? And that's a tough one to answer. I think my own interpretation of why so little is done in calibration is because when you can take that model out of the box and run it and put it up on a screen, and it looks great. I mean, I showed one; it looks fantastic. And I'm not sure that people think, oh, well, it looks so nice, it must be good. And even when you look at it, oh yeah, the cars are kind of doing what we want them to do. The answer, how long you should spend, I think it really depends on what you're after. If you're just looking at a planning type level of large scale, you can do a much simpler one. I know when we do safety, and I didn't talk about it, when we talk about safety simulations, and that's sort of the holy grail. If we do a simulation that say whether one device is safer than another, that gets real difficult because then you have to get into driver behavior and their accelerations and decelerations, so that takes a lot longer. My anecdotal one is it always takes a month. When we were doing it by hand, it took a month. When we're doing it with the computer, it takes a month. I don't know. I think there's something about, if people only walk so far, I think in calibration, people only have so much time.
So how much effort it takes to use the genetic algorithm to get what you want or what you observe in the field versus to do manual calibration?
Oh, it's hard to compare the two, right? So the question is how much longer, sorry.
Yeah, no, the question is, I'm doing the manual calibration, it takes so much time to simulate what's on the ground, right? You can use the genetic algorithm, and it might not hit exactly what I want, so I have to kind of redo to make sure that, I capture what I observe, right? So in your kind of practice, wherever you applied it, is time-wise, resources-wise, is it better or faster?
Right, so the question is on the manuals. On the manual side, it's going to take so much time to get a correct answer. You now have an automated one. How much time does it save you, right? I think is essentially the question. I guess I'm saying the opposite. What we end up doing is because we can run thousands, we can do it overnight, we can do it for a week, we can do it for 2 weeks. We can do a large, because you think of it as an optimization space, and the genetic algorithm looks at all of that. It does give you the opportunity to look at different solution sets and sort of hone in on some that work really well. So I guess my observation is, at least from our perspective, and I don't want to speak for others, is we spend the time to get a lot more observations and get a lot more comfortable with it. And we don't say, well, if it took us manually, it took us a month, now we can do it in a week. It usually takes about a month or 2 months to look through it and just make sure you're really comfortable. What it allows you to do is a larger search. Yeah. No, when the minute you decide that you're going to do statistics, and this is what I argue you should, because we have this empirical data that has these error bounds, we have this simulation with these error bounds. There is not one better than the other that you can say statistically. So you end up with a fairly large number that works statistically, but that gives you a starting point to go and find one that's internally consistent that you're comfortable with. And again, it goes back to my earlier point. We always say it was an art to calibration, and I think it still is. We have these tools, but at the end of the day, it's still someone going and saying, yes, this is a good model for what we want to do. Sure.
So you said the CA model is as good as the decent.
I did say that.
Do you want to say how much effort to build a CA model? And also, can you apply for a really congested, more complicated network?
But that network is extremely congested. So as I-10 is probably the second, third most congested one. So I said the CA model was as good as the VISM, but again, the reality is doing a pipe is relatively easy. So a simple CA model, I could probably go through and use a HCM and come up with, on a pipe, as good as a microsimulation. So yeah, we'd love to do some of the ones. I know was the other question as well, right? Can you do traffic signals? Can you do these other things? I think the open question, what always answered me is, how many parameters do you need? And when I first started doing this, I was actually doing the coding for the microsimulation model. So I know something about the development of it. And the first question we always got from people is, can you put in aggressive drivers and can you put in cautious drivers? And it's just, yeah, we can do it, but are we fooling ourselves? We put in all these things. I don't know that we have the data and the ability to say whether, to put all these parameters in. So sometimes I think we put them in so that the user can feel comfortable with them. But from a developer point of view, I don't think we can. The other classic one is if you look at the simulation, think of all the different commercial vehicles out there, the different attributes of them, how much they weigh, all their things. And you go into the microsimulation models, and there may be 3 or 4 types of commercial vehicles. I'm not criticizing it. I'm just saying there's a level of accuracy you're going to get out of your microsimulation model, and it probably should be reflected in almost everything you do, if that makes sense.
When you're doing choosing your best model,
yeah.
Are you trying to account for the difference in your ability to predict spatially versus temporally?
So the question came down to when you're picking your best model of all these statistically ones, are you worried more about spatial or are you worried more about temporal? And I'll go back to my original comment. It really depends on the application. So for example, we finished a project a few months ago on advanced warning devices. These are signs with signals that tell you when a light is about to change. And these are on high-speed rural intersections. So these cars are going 65, 60 miles per hour, coming into maybe the first signal in town. And so we have a sign that flashes and says, be prepared to stop. And most people will, because, so we're looking at, the efficacy of them. Are they safe from a statistical point of view, accidents and crashes? In our simulation, what I wanted to make sure about was the driver behavior that we were observing. So what's the speed profile of the vehicles as they come in? And we can track that for, 2,000 feet upstream of the intersection. Was the simulation model capturing that? So it was, in answer to your question, it was both spatial and temporal, but what I wanted was, simulation models don't give crashes, right? They give behavior changes, but I wanted to make sure that the driver behavior that we were modeling in the network, in the simulation, modeled what we were doing in the field. And once I had that, then we could go to the next step and say, well, what happens if you have more traffic? What happens if you change these things? So excellent question, but it depends on the application, but spatial and temporal is, are both important.
Any other questions?
Very good.
Great. So if that's the case, I would like to conclude.
Yeah.
I think thanks a lot, Larry,
thank you.
for your excellent lecture. Yesterday I went to the airport to pick him up. It took me 90 minutes from the airport, and he was already there waiting. And he told me he's been in Seattle several times. Every time he came with sunny. And yesterday I thought this time is not going to be sunny, but to look at today,
There we go.
Feel it like a sunshine problem, which is great. Actually, we do believe that reflector is going to set sunlight online for simulation research. And there are a lot of simulation work going on here. And I believe there are a lot of questions that this. So I have a bunch of questions, but I will wait until I maybe have dinner with Larry. So we actually prepare sometimes for interaction with Larry here. So we have food prepared, so maybe you can stay and keep talking to him until about maybe 4:20. So Megan, let's get out at 4:20.
We can actually do so.
Okay, so we have more time. So anyway, so let's give Larry another round of big applause. So thank you. And also thanks for those IT folks who travel along the distance. Those who made it come here. Thanks a lot. Okay, let's start the reception and pick up something to eat and drink.